Okay, hi everybody. So I gave out a sheet that has my new and improved office hours. And I also posted that on Blackboard. I tried to log into Starfish this morning because I think it still thinks of my office hours as last semester's, but it wouldn't let me log in. And so I have to figure that one out. So anyway, I do encourage you to come to my office hours. I've had a few students there this week, and I think it was, it's good to have contact and ask questions. And I hope to see more of you over there in building 2 in the Siberia of Rhode Island College on the East Campus. But anyway, okay, so I asked you to do these 5 at home if you hadn't done them in class. And I'm going to go over them. And if you have any questions, I hope that you ask them because you've had some chance to look at this at home, and maybe you have some questions. So, all right. So this is a matter of coming up with a formula. And the formula, as you know, is based on having the number of each, the cation and the anion, have the numbers of these ions such that the charges completely cancel, right? And that's what we worked on last time, or at the end of class. So for magnesium oxide, you would start by writing what the ion charges are for each of these. How do I know magnesium is +2? I use my periodic table. Everyone should have a periodic table with them here. I've given it out more than once. Mg is in the second column. We call it group 2 or group 2A. And everything in that group has a charge of +2 when it forms an ion. Oxide, oxygen is in group 6A. And as such, it needs 2 more electrons to have the number that the nearest rare noble gas has. And so its charge is -2. And when they come together, it's just one of each, 1 Mg2+ and 1 O2-. And so the name of the compound, or the formula of the compound, is just MgO. Simply, okay? Sodium is in what group in the periodic table is sodium? Yes, 1A. So its charge is +1. Sulfide. So this is sulfur with the "ide" ending that we use when we name compounds. It's right underneath oxygen, -2. So you see that you need 2 sodiums to balance the charge of 1 sulfide. And the formula, notice the formula is Na with a subscript of 2. So in other words, you never put a big letter 2 in a formula name. If you have 2 sodiums in one, what we call formula unit of sodium sulfide, then you put the 2 as a subscript. And also there's 1 sulfide, but you don't put a 1 as a subscript. There's no subscript. It's assumed to be 1. So this is sodium sulfide. Okay. Now, what about cobalt? Cobalt 2. What's the charge on that cobalt ion? It's +2. The number here gives it away. Whatever the number is in parentheses, that's the charge on that metal ion. That's a cation. Always metals are going to be the cations, the positively charged ions. Chloride. Where's that in the periodic table? Just shout it out. Don't have to raise your hand. Group 7. How many electrons does it need? It needs 1 electron to be like the next rare gas. So its charge is -1. So that means that we would need 2 Cls to balance out the cobalt's charge. So you would have 1 cobalt ion and 2 chlorides per formula unit of CoCl2. Now, why do I call this a formula unit and not a molecule? What type of compound? Oh, yes, go ahead. The charge is balanced, yes, but it's an ionic compound, and ionic compounds do not exist as clusters of atoms that are separate from each other. I showed you some pictures last time of ionic and molecular. Let's see if I can get them back here. I don't know where they are. Here. Okay, these are ionic compounds. They are continuous arrays of different colored, meaning different charges and different of ions. That is a very different look than these. You see how these, you have literally clusters of atoms. Here you have very large clusters. Here you have a cluster of just 3, but they're separated from each other. You have these clusters that are separate entities. They're like individual clusters of atoms that we call molecules. In an ionic compound, all you have is one after the other of these ions. Yes.
Like one thing they all like I know what makes one molecule.
Oh, okay. So maybe you're what holds them together? Is that what you mean? Notice in this picture, there are these dotted lines. You see, those are, yes, these are actually intermolecular forces, which are weaker than ionic bonds. So those compounds like melt at lower temperatures, things like that. But that's chemistry 104. Okay. So anyway, good question though. Iron 3 is a dead giveaway. What is the charge on iron 3? It's +3. And oxide, again, just like over here, is O2 minus. And now, we have to figure out, well, how many? It's like in math when you find the least common multiple or something like that. You have to be able to balance a charge. And so this is where you might want to use something we call the crisscross method. You take the 3 from here and the 2 from here. So that means 2 Fe3 plus and 2 and 3 O2 minus. So this 3 came down here and this 2 went down there. And so you end up with Fe2O3. Okay. So you would have, did I do that wrong? No, I did that right. 2 Fe3 plus and 3 O2. Nope, Fe2. See, Fe is 3 plus, so 2 times +3 is +6, and 3 times -2 is -6, and the sum equals 0. So the 3 on this is a good point, actually. The 3 here goes with the charge. It does not go with the number of that ion. Be careful. That's a very common mistake, to see that 3 and say, oh, that's a 3 subscript. No, it's not. Okay, so this would be Fe2O3. That's your rust. And silver chloride is pretty easy, except silver you cannot get from the periodic table. Silver, you have to look at the chart of the transition metal ions, which is on a page that looks like this, that has a little periodic table with a B on your previous set of handouts. The B groups, the transition metals, are harder to predict. And when there's when a particular element can form 2 different ions, we use the like cobalt 2, cobalt 3, if it could be 2 plus or 3 plus, but silver can only be 1 plus. So silver you can't get from the name. So you just need to know that it's Ag plus. But I'll give you this chart so you don't have to really memorize it. And chloride, we already figured out that that's 1 minus, okay? And when you put these together, you get the simple AgCl. Okay, so now we have to go on and sort of move up to the next step. But before I do, does anyone have a question about any of these? Okay, let's move on. All right, so next we have this barium hydroxide, and we know what barium is. That's not a problem. Barium is in group 2A, so it's Ba2 plus, but hydroxide is a bit of a puzzler because it doesn't follow. It's not the name of a of an element with an "ide" ending. It's actually got kind of some hide and some ox. So you're thinking hydrogen, oxygen. So what is hydroxide? Yes, I was actually asking a rhetorical question, but that's fine. I'm glad you told me. It's a polyatomic ion. It's got more than one atom bonded together. And what's interesting is that this is a covalent bond between O and H that has acquired an extra negative charge. So in other words, oxygen provides a certain number of electrons. The number of electrons is from the periodic table. You could see its atomic number is 8. Oxygen has 8 protons. It also has 8 electrons when it's neutral. Hydrogen has 1. So that would mean that you would expect that OH would just have 8 plus 1 or 9 electrons. But actually, this guy has 1 extra one, has 10. So we put the negative charge out here, like I've shown you. This is a covalent bond. Do you remember what a covalent bond is? What? Yes, a covalent bond means that electrons are shared. Already, this is starting to bug me, and I plugged it in, so it's not that today. So that means electrons are shared. I'm glad you think it's funny. I do too, actually. All right, so that's an example of that's the simplest example of a polyatomic, more than one atom ion. Okay, if we look at this next one here, ammonium nitrate. Now, is this N3 minus? Is that what that is? What is this? What would this ion be called? When you have an ion from just one nonmetal, okay, you have the "ide" ending. This is called nitride. So you need to remember that. Nitride goes with monatomic ions, okay, nonmetals. So we have chloride, bromide, oxide. Okay, these all have "ide" endings. But this is nitrate. And when you have the 8 or "ite" endings, these are combinations with oxygen. And so nitrate is actually another polyatomic ion. It's actually a nitrogen that's covalently bonded to 3 oxygens. Its structure is really more like this, like it's a 120-degree angle. You don't have to know this. This is later in the course, and it carries 1 extra negative charge. I don't like the way that looks. There. So this is nitrate ion. Okay, and another example is sulfate. And sulfur with 4 oxygens. These are all covalent bonds here, sharing electrons. And this carries a charge of -2. So it has 2 extra charges beyond what the sulfur and the 4 oxygen atoms would contribute. So how do we do this? How do we do barium? And we did barium hydroxide. Okay, barium hydroxide then is made from a barium ion. The barium ion we're familiar with because it's in the group 2 of the periodic table. Or 2A, whichever numbering system you use. And so its charge is going to be +2. Hydroxide is OH minus. Now, I want to call your attention to another chart that I've given you. It's in this packet here. The one that has the mass spec on the front. You go sort of towards the back. On the back of the page that has the nice pictures, that I just showed you of ionic and molecular compounds on the back is a chart, and it says common polyatomic ions. Okay, it used to be that we used to make students memorize these, but in the internet age, I have decided there's no point in memorizing these. So I will give you this chart, but I will tell you that it's a very good idea to familiarize yourself with this chart. In other words, to use it and try to sort of get familiar with where these ions and you know, so that when you take a quiz, you're not looking at it for the first time. Okay. So you look at this common polyatomic ion chart. And in the next example, so we're up to here. Barium hydroxide was 1 barium ion. Oh, and there would be, since OH is just OH minus, how many of those would we need to balance the 1 barium ion? Balance the barium ion. 2 OH minus. So one formula unit of this ionic compound has 1 barium and 2 OHs, 2 OH minuses, and we need to use a parentheses there. Okay, if you wrote it this way, that's incorrect. You must put the parentheses here because you're taking both the O and the H twice. Yeah. No, sorry. But you know what? It's on the chart. It's on the chart. I mean, it's just, yeah, there's just do what's on the chart. Ammonium nitrate. Okay, so nitrate I've talked to you about. I told you nitrate was this guy, NO3 minus, right here. But what about ammonium? And if you look on your polyatomic chart here, ammonium is the first one. And this is the only cation on this list. In other words, when you have an ionic compound in Chem 103, that compound is going to usually have a metal ion and then an anion. Like, so for example, it would be NaCl, that's a metal ion, or MgCl2 or something, that's a metal ion. The only time it won't be a metal ion is if it's an ammonium. So NH4Cl is also an ionic compound. So ammonium is the only cation that is a polyatomic ion that we use here, well, in Chem 103. So when you see a name that has ammonium, you will know that they're talking about the ammonium ion, which is NH4 plus. So let's go back here. So we have NH4 plus, and we have NO3 minus, okay? So that's ammonium nitrate, and they're each 1 plus. So we'd have 1 NH4 plus and 1 NO3 minus. And when you put that together, that's just NH4 NO3. I don't need parentheses because I'm not taking any of them more than once. It's just one of each. But notice when you write a formula, there are no charges in the formula. The charges have canceled. And if you have a polyatomic ion that's taken more than once, you must put a parentheses. Okay, but there's no need to put it there for NH4NO3. Yeah.
You just put the parentheses anyway, just to
Like if you're just insecure, you want to write it like this. Yeah. Don't do it, but I wouldn't mark it wrong, you know. Yeah. It's just bad form, you know. You want to have good form. All right, so so what I'd like you to do is actually take some time to work on activity 3. The rest of it, if you've already done it, then you could work on activity 4. Activity 4, I'm going to collect as a special problem. There's a lot of stuff on there, but I'll collect that on Tuesday. What is Tuesday? The 19th. Take it.
This one right here.
Those are the spares.
Oh, these are the stairs. I didn't-
Yeah. Okay. So let's see, did I not? Oh, I do have it here. Okay, so this is the rest of. So if you didn't bring it with you, you could look at it up here. This is the rest of activity 3. So I'm gonna come around, I'm gonna give us some time to work on this. And then I have some more stuff to tell you to finish off about ionic compounds and start on the next thing. And then I'll talk about molecular compounds a little. I think you have that already. It's this mass spec on the front. Oh, yeah. Yeah, okay, right. We're working on it. We're working on it.
No. What's it- The polyatomic.
It's in there with the mass spec.
Oh, I thought it.
That's the part. Okay, so while you're working on this, I did type out a handout of the day, but I want to add 2 problems here. So I'd like you to get a piece of paper. And I'll write HOD on it and put today's date, which is 9/14/23. And I'd like you to do zinc bromide and cobalt 2 hydroxide. So it's what I want you to do is exactly what you do in this exercise. Okay, I want the number of ions in a formula unit and the formula. And this one you will turn in today for the handout of the day. Hold on to it, give it to me at the end because I may put something else on it. Okay. So that's what we're working. Sorry? And cobalt hydroxide, yeah. And I'm going to come around and look at your activity 3. And if you were fantastic and did that all already, I'll look at activity 4. But maybe you should have me check your activity 3. I don't know. Is that better? Can you see it? Okay. Yeah, the special problem for Tuesday. I did it before. Yeah. All right. Give me this chart.
That's what.
All right, I want to just make an announcement about lead. Lead is +2, DD is +2. I'm gonna have to add it to the chart. It's not technically a transition metal. It's an exception, but, I'll put it on the calendar for it. Okay.
Did you? Then you keep the pretty stuff, and you don't have.
Oh, well, because it's just the O3 is just everything.
Yeah.
In here. Never put a big number. Two and two. Oh, okay. Then you must be getting done, a lot of talking, if it's about chemistry, that's fine. I'm gonna go a minute front.
Yeah.
No, you never have capital numbers,
Okay.
big numbers in a formula, you only have subscripts. Those are right.
Okay.
Yeah.
You don't.
You know, you put the parentheses instead of- Exactly. Well, you have it both ways.
Oh, I tried to.
Oh, I see, you have it. So this is PA, two.
I don't do that here.
No, here you're telling me what is in one of these.
Okay, great.
So, don't get on the. So five, is necessarily not just. Okay. All right.
Okay, so moving along. I have another, so anyway, remember I told you that, that activity 4, I'm going to make a special problem. Activity 4 has a lot of what you just did in activity 3, but it has some where it gives you the formula and it asks you for the name. Okay, so you have to know how to do that as well. So I'll take that on next time. So what I wanted to do was tell you a little bit about a special kind of ionic compound that we call a hydrate. Okay. Is there a question? Because I prefer to answer it than to just listen to you talk about it. Yeah.
We do like the polyatomic ions or whatever,
Yeah.
and it's more than one.
More than one. Yeah.
So the outside of
All right. Let me just show you with an example. Okay. Like calcium phosphate. That was Ca2 plus and PO4 3 minus. You get that from the chart, the PO4, right? And the calcium is in the second group, so it's +2. So you know that you're going to need 3 of these and 2 of these in a formula unit. So that's Ca3 paren PO4 2. So the parentheses indicates that you take the entire polyatomic ion, the number that you put over here. So there are no, I call them capital numbers, but you would not do it this way. Don't give me this. This is going to be marked wrong. Okay. It's just not a proper formula. Does that answer your question? Okay, good. All right. So there, you need to practice that. So don't think that because you practiced it for 10 minutes in class that it's enough. You should do activity 3, you should do activity 4, then you should go back with a clean copy of activity 3 and do it all over again. That's what I think you should do. That's what you have to do in this class, because we don't have time in class to do problems over and over and over again. If you're having problems, come to my office. I'll show you some stuff. I'll put you in a room and you could work on problems and I'll come and check on you. Maybe there'll be other students in there. That might be a nice thing, so think of me when you are having trouble. Okay, so next week in your lab, you're going to need to know what a hydrate is. And hydrates are kind of a special class of ionic compounds. And I'm going to show you this picture here. I guess I got to blow it up a little bit. It's a little small. Oops, that didn't work. Okay. So this is copper sulfate, CuSO4. So if you were going to name it, it would be copper 2 sulfate. How do I know the name is copper 2 sulfate? if I'm given the formula CuSO4, how do I know? Yes. Yes, he says because sulfate has two negative charges. So we know that copper must have two positives because this formula has just one of each. So it can't be Cu plus. Okay. And if you look at your transition metal chart of ions, you will see that copper could be +1 or +2, but it's copper 2 sulfate because we know it balances with 1 sulfate, which is on your other chart. And I'll always give you those charts. So there's not a whole lot of stress of memorizing, but you have to know how to use them. Okay. So copper sulfate here, I'm going to tell you that the copper ions in this picture are the copper colored are the copper colored circles. The sulfur is the yellow and the oxygens are the red. Oxygens are pretty much always red. So you could see that what you have in here is like a continuous array of here's here, if you look at this, for example, you could see a sulfur with a couple of oxygens and the other oxygens are on the other side. Okay, so you have a sulfate, SO4, and a Cu2 plus, and a sulfate and a copper, and it goes on continuously, and it looks kind of pretty, I think. I think we could have a textile with this design on it, and maybe some geeky chemist would buy it, but I don't know. Now, this guy here is also got copper sulfate, but it has water molecules that are incorporated into the crystal structure. So that's what a hydrate is an ionic compound with H2Os embedded sort of into the crystal structure, incorporated. How do I know that there's waters in here? Well, if you look, you could see this, you could see the red with the two white, all of these are water molecules. There's a ton of water molecules in here. The white are the hydrogens of the waters. So every time you see something white in here, you're seeing hydrogen of a water molecule. And it turns out that there are actually 5 water molecules for every copper sulfate in this copper sulfate hydrated salt. These have pretty different appearances. Anhydrous copper sulfate is really very pale in color. But when you have the hydrated salt, it's a beautiful bright blue. So what I want to do is tell you how to name a hydrate. You're going to see a hydrate in lab on Tuesday and Thursday next week. So I thought I should tell you about them. So what I want to tell you is how to name a hydrate. Naming hydrate. So what you do, here it is. Let me see. Yeah, I think I made that too big. Naming hydrates. So what you do is you use the name of the ionic compound followed by a prefix that indicates the number of molecules of water per formula unit of that hydrate. So followed by a prefix indicating the number of water molecules per formula unit of the compound. And then, so followed by the term hydrate. So it's best to just give you an example. So let me, so it's the name of the ionic compound, followed by a prefix, followed by the word hydrate. And the prefix indicates the number of water molecules. So COCl2 dot. This is a dot that we put in the formula to indicate the number of water molecules per cobalt chloride. So here you could see that you have 6 water molecules per formula unit of H2O in the crystal structure. So this would be, okay, what's the name of this compound? Okay, almost right. It would be cobalt 2 chloride, because if you look at your sheet of transition metal ions, you will see that cobalt can be +2 or +3. And if you don't indicate it, then you don't know. I know it's got to be +2. How do I know it's +2? Chloride is -1, and there's 2 of them. So that means it's got to balance a -2. Okay, so cobalt 2 chloride. And now what about those prefixes? So these are the prefixes. Mono means 1, di means 2, tri means 3, tetra is 4, penta is 5. Anybody know 6? No, it's hexa. Good guess though. Hepta is 7. Nana is 9. Deca would be 10, but enough already, you know. So this would be cobalt 2 chloride, hexa hydrate. So that's a very long name. All right, let me give you another one. What about that one? What's Cu? Copper. Look on the transition metal ion chart. What do you see about copper? It can be what? It can be +1 or +2. What is it going to, what is it here? Right, because chloride is -1, and you have 2 of them, so that's -2. So the Cu must be +2 to balance it. So we have copper 2 chloride, and then what do I add after that? Dihydrate. Okay. Good. So that's your quick and dirty lesson in hydrates. And I'm sure you'll get a little more info on them next week when you're in lab. Okay. All right. So I want to spend just a little bit of time on molecular compounds, on naming molecular compounds. We spent an inordinate amount of time on molecular compounds. But for molecular compounds, just to go over what they are before I go into the naming, we know that these contain individual molecules that are really separate clusters of atoms, separate from one another. And basically, they consist of 2 or more nonmetals, or sometimes metalloids, covalently bonded to one another. Okay, so I want to point out here that molecular compounds do not contain metals. So if you're asked to tell the difference, what is this compound? Is it ionic or is it molecular? If you see a metal, that tells you it's ionic, because molecular compounds do not, at least in Chem 103, contain metals. Nonmetals and metalloids are in molecular compounds. Mostly it's 2 or more nonmetals. Okay. All right. So how do we name them? Well, there's a giant book in the conference room of the physical sciences department. It's about literally this thick, and a good portion of it has names of many compounds There are so many compounds and so many names, so we don't do that in general chemistry. We only do names of what we call binary compounds. And these are binary molecular compounds have only 2 elements. We don't do anything more complicated than that. Let me get some more space here. Okay. All right. Now, when we name these, so maybe let's recall for ionic compounds, the number of ions never enters the name. Okay, so let me give you an example and this is to contrast to molecular compounds. For ionic compounds, if you have MgCl2, the name is magnesium chloride. The fact that this is a 2 never enters into the name. There are no numbers in the names. Now, why do you think that might be? Why don't you have to put a number in the name to tell the person what compound you're talking about? The charges are known, so what does that mean? What about MgCl2? Can you have MgCl? Yes. Yeah, that's right. They're always balanced. The charges have to balance, and there's only one way to let those charges balance and have the most reduced form for that formula. So we know that magnesium chloride has to be MgCl2. It can't be MgCl. It can't be Mg2Cl. It has to be MgCl2 because the charges must balance. That is not so for molecular compounds. And the reason for that is because when you have sharing of electrons, there is more than one way that electrons can be shared. So for molecular compounds, electrons are shared, and there is often more than one way for electrons to be shared. And let me give you a nice example. If you have nitrogen and oxygen, you can have the following compounds: N2O, NO2, and I'm only giving you some of them, N2O5. So there's more than one way for electrons to be shared, okay? So the name tells you how many you have of each. Okay, so this one, these all 3 have different names. So let me tell you how to name these compounds. Okay, so when you naming a molecular, this is only a binary molecular compound. This is what it is. It starts with the prefix for the first element, which is that mono, di, tri, etc. The same prefixes we just talked about for the hydrates. Then it's the name of the first element. So that prefix is for that first element. How many of them are there? Then there's a prefix for the second element. But for the second element, we use a shortened name for the second element, and we put the "ide" ending on it. All right, it sounds really complicated, but it's really not that complicated. So this guy here would be di, right? The prefix di, and the element is nitrogen. Monoxide. So see how you have the di and the mono, those prefixes. You have the "ide" ending here. You have the shortened name, and you have the name of the first element. So what would this one be called with that same thing? Say it again. Yeah, this is actually called nitrogen dioxide. But going by this formula, you would think it would be mononitrogen dioxide, but you drop the mono if it's for the first element. That's another little thing, okay? What would this one be called then? The third one here. Dinitrogen pentoxide. Exactly. Perfect. Okay, so what I have is another little exercise here for you to name these using that same method, okay? And how about putting these two on the HOD? Okay, add that to the handout of the day. Which is today a piece of paper of the day. So just continue. Let me do the first one for you. This would be sulfur, hex, fluoride. Okay. Well, this one we did already, so you don't have to, these we did actually.
Yeah, that's what I think. Right on the contact. You can't have more than one, whatever. Okay.
All right, these guys here, I'll take, I'm actually just do them at home, not as a special problem, but you have, we don't have time to do those in the class, but it's good practice. And I think that this word notice here fell off your handout. Is that true? Is it just a colon? Yeah. Weird. Well, write notice. There are no metals in these compounds. These are molecular compounds. You will not see metals in molecular compounds. Okay. Now, down here is another exercise for you to figure out whether these compounds are ionic or molecular, and then give the name. Okay. So this one, let's just do a few of these. What about this one? Remember that hydrogen, even though it's on the left side of the periodic table, it's a non-metal. It's the exception. So these are all non-metals. Do you see that? Give me a nod if you see that. Yeah. So there are all non-metals here. So what type of compound is this? It's going to be molecular. Ionic has to have a metal. So an ionic compound have a metal. What is the other thing it can have? It doesn't have a metal. NH4 plus, ammonium. A metal or ammonium. And so name or formula, can we give it? No, it's not binary, so we don't have to know those names. It's not binary, so we can't. It's non-binary. So here we have calcium with this weird thing in parentheses. Uh-oh, I don't think, is that on the chart? Is that on the chart? What is it called? It's called bicarbonate. No. This one, this is a molecular compound that is binary. Binary just means two elements. So there are plenty of molecular compounds with two elements, plenty of binary molecular compounds. All right, but this thing I underlined here is the bicarbonate ion. What's the name of this ion? So this is calcium bicarbonate. Notice the 2 is not in the name. This compound has a metal. So what type of compound are we talking about here? It's a metal ion, right? What does that mean it has to be? It has to be ionic. Right. Metal or ammonium. Yeah. Now, what about what type of atoms are these? This is a metalloid. And this is a non-metal. So what type of compound does it have to be? molecular. And then you use the naming that we use for molecular compounds. Boron, trichloride. Now, this is a trick question. Ammonia, notice it's not ammonium. And ammonia is not the same as ammonium. Okay? Ammonia, you have to memorize the formula. It's a very important compound for us chemists. Its formula is NH3. So it's not nitrogen trihydride, although you could call it that. We give it the name ammonia. And it's molecular. So it's not ammonium. But here we have at H, I know there's no G, but that's oh well. What about this compound? Is this ionic or molecular? It's ionic because it has ammonium, okay? And ammonium is NH4. And carbonate, if you look it up, is CO3 2 minus. So what would the formula be? To NH4 2 CO3. That's ionic. What about barium hydroxide? We've used that example today, so is that ionic or molecular? What's the dead, what gives it dead away that it's ionic? It has a metal. This is a metal that makes it ionic. And we did this example earlier. And this is one of those crazy hydrates. And hydrates are ionic, even though they have some molecules of water inside them. This is copper 2 sulfate. I know it's copper 2 because SO4 is 2 negative, and it's just balanced by a Cu2 plus. And this is pentahydrate. Yeah. All the ones we learn about. I don't know. I don't think there's any others. Yeah. Okay. So, okay. So now I have to switch gears completely and talk to you about the next topic, which I have to find. Okay. And it's very important what we're doing next. Everything is very important, I know, at the beginning of this course. So we're starting chapter 3. Chapter 3 deals with mass relationships in chemistry. That's not what the chapter is called, but that's really what this chapter is about. And I'm sorry to have to make such a big gear shift right in the middle of class, which is why I think that classes should be 50 minutes, but that's just my opinion. Nobody listens to me. Okay, so I want to show you just like what we learned about the periodic table. If you have hydrogen, we have a 1 up here and we have a mass down here. And so what this tells you, what the periodic table gives you is the average mass here. This is the average mass of 1 hydrogen atom. And this is in atomic mass units, okay? Just like if I talk about carbon with the atomic number of 6, 12.01. This number is the average mass of a carbon atom, of 1 carbon atom in atomic mass units. That's what AMU is. Now, here's the thing. Atomic mass units are fantastic if you're talking about the mass of a single atom, or maybe even 5 or 10 atoms, but we don't deal with quantities like that in the lab, right? When we go to weigh out a certain amount of carbon or anything in the lab, we don't, the scale doesn't measure atomic mass units. We have so much carbon, so many carbon atoms in there that we have to use grams. We weigh things out in grams, okay? So to do practical chemistry, which we really want you to be able to do, and we are going to move into the lab soon, they're almost ready. To do practical chemistry, we need to deal with macroscopic, seeable, holdable, handleable amounts of each of these elements and compounds and things like that. We need to deal with macroscopic, meaning, large things we can hold on to, macroscopic amounts of chemicals, not, single atoms. So really, atomic mass units are sort of useless in the lab. Now it won't let me erase what I didn't want there. Okay. So but the thing is, it would be nice if the masses of things from the periodic table, it would be nice if those numbers that are underneath each of those elements, if they corresponded, it would be nice if those numbers could be associated with the given element, but instead of being in atomic mass units, we could talk about it in grams. So it would be nice if 1.008 grams of hydrogen was an amount that we knew, how many atoms it was, okay? It would be nice if 12.01 grams could represent an amount of carbon that we use over and over again. So we'd like to be able to associate. We'd like to associate 1.008 grams instead of AMU with hydrogen, and 12.01 grams with carbon. So how are we going to do that? Okay. And the way we're going to do that is we're going to figure out how many atoms of hydrogen is in 1.008 grams. So let's write that down. How many atoms of hydrogen are in 1.008 grams? And then we're going to call that something. And we're going to call that, anybody know? We call that a mole, okay? How many atoms are in 1.008 grams? And we're going to call that number a mole. That's where we're heading here. We're going to find out how many atoms of carbon are in 12.01 grams. Okay, so let me show you how we can do that. And we can use dimensional analysis to do this because we know certain conversions. So let's go over what we know, what is known. We know how to go from grams to atomic mass units. We know that 1.66054 times 10 to the negative 24 grams is 1 atomic mass unit. They're both units of mass, and we can convert between them. Okay, this gives us a conversion factor between grams and AMU. We also know that one hydrogen atom has a mass of 1.008 atomic mass units. Okay, so that tells us that we could go from atoms of hydrogen to atomic mass units. So now let me show you what I'm going to do here. I'm going to start with the mass of with a mass of 1.008 grams of hydrogen. So I'm going to use dimensional analysis. I'm going to go 1.008 grams of hydrogen. And I know how to convert that to atomic mass units. If you go up here, you see I have this relationship here. So that means that I could put 1 AMU on top, and that mass, that's 1 AMU in grams, on the bottom. You see, if those are equal, then if I divide both sides by this number, like I've done many times before, it's equal to 1, and I could use it as a conversion factor. Okay, so that's what I'm doing here. I'm using this conversion factor. And my grams are going to cancel. And I will be left with, if I did this calculation, that would be the number of atomic mass units in 1.008 grams. But I don't want to know that. I want to know how many atoms that is. Well, I can use this other information. 1 hydrogen atom, 1.008 AMU, because these things are equal. So this is a conversion factor that I could use. So I'm going to use it. So my AMUs are going to cancel. And look, I went from what I wanted. I went from grams of hydrogen. I got rid of grams here by canceling. I found AMU. Then I canceled AMU, and I end up with what I want, which is the number of hydrogen atoms. And when you do this calculation, you get 6.022 times 10 to the 23rd hydrogen atoms. So this is the number of hydrogen atoms in 1.008 grams. And the reason that's significant is because that is the number on the periodic table underneath hydrogen. We call this a mole, okay? And we can do this with any element on the periodic table. The number underneath the element corresponds to this many atoms in the number of grams that you see in that box. So let's do this for carbon. One more example, 12.01 grams of carbon. Remember, on the periodic table, you have 12.01 there. So 12.01 grams of carbon. How many atoms is that? I haven't really proved that it's also the same number, but it is. And I do the same calculation. I go from grams to atomic mass units using the same conversion. And then looking at the periodic table, it tells me 12.01, oops. AMU is 1 carbon atom. So you do this multiplication, you cancel grams, you cancel AMUs, and it turns out that you get 6.022 times 10 to the 23rd carbon atoms in 12.01 grams, just like the periodic table tells you. So what this means is that you could take that periodic table that you have, and every mass that you see written under an element is the mass of this many atoms of that element, which we call a mole, okay? So this is 1 mole of carbon. This is the number of carbon atoms in 1 mole of carbon. So you could think about a mole as just a really big number. It's kind of like a dozen, only bigger. So instead of saying a dozen carbon atoms, you need way more than a dozen carbon atoms to get 12.01 grams from the periodic table. You need 6.02 times 10 to the 23rd carbon atoms. Yes. No, mole is mole. Yeah.
So it's carbon per gram.
That's carbon atom, 6 times 10 to the 23rd carbon atoms per mole. Per 12.01 grams. I'm about to do this here. Let me show you. So 1 mole of carbon has 6.02 times 10 to the 23rd atoms of carbon and is also 12.01 grams. These are all equivalent. So we will be able to establish equivalence ratios. Remember, conversion factors or equivalence ratios for all of these things. So I'll be able to use things like 1 mole of carbon, 12.01 grams. 12.01 grams, 1 mole of carbon, right? Because these are all equivalent. I could multiply by the ratio of any 2 of them. There, and all of those ratios are 1. So I can multiply by them and just change whether it's moles or grams. I could also put 1 mole, 6.02 times 10 to the 23rd atoms. So I'll be able to switch between moles and atoms. 6.02 times 10 to the 23rd atoms, 1 mole. Okay, things like that. I can, and that's for carbon. I could do the same or similar for hydrogen. 1 mole of hydrogen is 6.02 times 10 to the 23rd hydrogen atoms, or 1.008 grams, you know, what you see in the periodic table under hydrogen, okay? And this leads to conversion factors or equivalence relations like this. And then you could do the one with the atoms. And the reverse as well. So this leads to something that we call the molar mass. The molar mass is the mass of 1 mole, okay? So the molar, oops, I'm not doing that. That's the ghost. Molar mass is the mass of 1 mole. For carbon, it's 12.01 grams per mole. So we could write it that way, or we could write it like this. So we call it the molar mass. That's for carbon. For hydrogen, 1.008 grams per 1 mole. 1.008 grams per mole. And so you could use this molar mass. You could use it that way. You could use it the other way. You could flip it. And you use it to convert from grams to moles and from moles to grams. Okay. So let me give you a quick example here. If I want to find out what is the mass of 3 moles of platinum, PT. So what do I look for to do this problem? Where do I have to go? Yeah, PT, haha, platinum periodic table. Periodic table. Look up platinum. It's number 78, atomic number 78. So the mass, 195.1. Okay, that's the mass on the periodic table. So that means it's 195.1 grams per mole. That's the molar mass of platinum. Okay, so now that's one way to write it. This is the other way to write it. Or this way. Yeah, you could, as long as you know that that means one. Yeah. Okay, so now if I want to take 3 moles, which I abbreviate MOL, okay, and I want to convert it to grams, which one of these do I use? This one or this one? With the 1 mole on the bottom, right? So when you're converting from moles to grams, you basically multiply by the molar mass. But if you use dimensional analysis, you never have to think that way. You just put it in such a way that the units cancel appropriately. Okay, and this comes out to 585 grams of platinum. Boy, I'd like to have that. That must be worth a lot of money. Okay, similarly, if I ask, how many moles of platinum are there in 2,171 grams? Okay. How many moles of platinum are there in that many grams? I would start with what I'm given, 2,171 grams. And now, which one do I put in here? The first or the second? Right, because I want to cancel grams. Okay, and so grams will cancel. And now you're dividing by the molar mass to go from grams to moles. So this should look something like a little familiar, because it's a lot like when you're converting from centimeters to inches or something like that. You put the unit you want to get rid of on the bottom and you do your canceling. This comes out to 11.13 moles. But now let's take this a step further. Supposing I say, well, how many atoms of platinum is that? So I'll start with 11.13 moles. And now, okay, so how do I go from moles to atoms? Well, 1 mole is 6.02 times 10 to the 23rd atoms. So that means I can divide both by 1 mole. If I could use this is equal to 1. Did it again.
So you did get that.
So can you talk a little louder?
Where did you get this?
Oh, that's Avogadro's number.
Okay.
So I can use it this way or the other way. Oh, that's the number of grams in 1.66054 times 10 to the minus 24th grams per 1 atomic mass unit. Yeah, that's a different conversion. This is the one you use here. So I could put my 6.02 times 10 to the 23rd atoms per 1 mole. Okay. .02 times 10 to the 23rd atoms per mole. And now if I do my math here, my moles cancel and I end up with 6.70 times 10 to the 24th atoms of platinum. Okay, so you might want to know that. So we have ways now of going between grams and moles, moles and atoms. So that's the way it works for atoms. But this doesn't only work for atoms, it also works for molecules. So I guess my next question is, what about molecules? Okay, what about molecules? Compounds. So let's do an example. C2H4O2. Here's a molecule, okay? This represents one molecule of a compound. And in this molecule, you have 2 carbons, you have 4 hydrogens, and you have 2 oxygens in a molecule. So if I were going to figure out the mass of one molecule, I would go to my periodic table. I would take 2 times 12.01, and that would be 24.02, not 2.02, atomic mass units. I would take, this is something you should know how to do from earlier, although you haven't done it all that much yet. And 2 oxygens would be 2 times 16, or 32. And you would add this up, and you would get 60.05 atomic mass units. Okay, this is actually the example I do on the first page of activity 1 information for chapter 3. Okay, so this is the mass of one C2H4O2 molecule. So remember what we did with the elements in the periodic table. We wanted the mass underneath each box in grams to represent a certain amount of that material. Well, we want to do the same thing with molecules. We want to say, how many molecules are in 60.05 grams, not AMUs, but grams of C2H4O2? What do you think the answer to that question is going to be? Say it. 60.05 grams? No. One is in 60.05 AMU, but in 60.05 grams, it's going to end up being a mole. Because so let me show you. Let me just go through it. 60.05 grams. I'm going to convert grams to atomic mass units. 1 AMU is that funny number. Notice how few grams, 10 to the negative 24 grams for an AMU. Okay, and we also know that 12.01 atomic mass units, oh, sorry, 60.05. I'm back to carbon in my head. 60.05 atomic mass units is the mass of one carbon atom. So now I could cancel grams, cancel AMU, and guess what? This comes out 6.02 times 10 to the 23rd. Oh, sorry, I don't mean a carbon atom, duh. I mean one C2H4O2 molecule. Yeah. Not so good. If you did, you'd get confused with moles. Yeah. So let me just say that you never have to do a calculation like this again. All you have to do is remember that if you use the masses on the periodic table in grams and you add them up to get the mass of a compound in grams, that is 1 mole of the compound. And so what we have here, this 60.05 grams is the molar mass of C2H4O2. It is the mass of 1 mole, which is also 6.02 times 10 to the 23rd molecules. So this means that you could go from moles to grams and grams to moles. of any compound whose mass you can figure out from those numbers on the bottom of each element in the periodic table. Okay, we can convert back and forth. And this is the quantity that we use, grams per mole. You could write it this way. Some problems you need to use it that way. Some problems you need to use it this way. It depends on whether you're converting grams to moles or moles to grams.
So the 6.05 grams is the molar mass of that molecule, and then you wrote the mass of 1 mole times that number.
It's just equal to that. The mass of 1 mole is that number. Yeah. You could also use 1 mole, 6.02 times 10 to the 23rd molecules, or the other way around. I'm just going to do an example of this with that. Suppose you have 361 grams of C2H4O2. The question is, how many moles is this? So I would start with my 361 grams. And I would put my molar mass on the bottom, because that will allow me to cancel the grams. And so 361 divided by 60.05 is 6.01 moles. And if you want to know how many molecules, what do you do then? What do I put in here? Molecules per 1 mole. And so you're going to get a gigantic number. Okay. Yeah. So I just want to say that, you know, this material is difficult. It requires a lot of practice. So you do need to practice. You need to spend a substantial amount of time on this class outside of class to really grasp everything. So you need to study what we did today. And yeah, and I'm available if you need help. I gave you my office hours. I didn't do that because I don't want you to come. So have a good afternoon. Oh, I'm posting chapter 2 graded problem set. That graded problem set from chapter 1 is due tonight at midnight. Has everybody been following Blackboard? If you need more time, you better let me know soon. Yeah. Yeah, give me the handout of the day before you go. You need to get credit for coming.